Welcome all. Karim. Let's continue this playlist of statistics with key questions, the most frequent questions in statistics. Let's start in this session with this first question we have here in this notebook. So, question one: what are the effects of width of confidence interval? So, as we know, in informational statistics, this confidence interval is very important. Well, if we see the answer here, the confidence interval used for decision making. That means the decision we're gonna make is depend of width of confidence interval. So as confidence level increases, the width of confidence interval also increases. I mean, if we have this confidence level is increased, automatically the width of confidence interval also will be increased. As the width of confidence interval increase, we tend to get less information. I mean, if we have this width of confidence interval, we can use some provided information to make in our decision. So less information, I mean, with confidence interval, also we have higher risk. If this confidence interval, we have higher risk to predict some wrong or making some wrong decision. So it's important to choose appropriate confidence interval depending on the specific requirement, the analysis, and available data. I mean, this confidence interval is firstly dependent of available data, so we cannot increase the width of confidence interval without having enough data to do that. This is the first part. The second one is depend on domain or specific requirement, because if we take in the area of drugs, for example, the rate of risk, I mean alpha, this will be small. Okay, by default it's 5%, but in drugs, when we try to produce the drugs or test or make some tests in drugs, okay, I mean hypothesis testing, so at this time it should be interest to this rate of risk. I mean, this should not be 5%, it will be less than that. Okay. The question two, mention the relationship between standard error and the margin of error. Well, as the standard error increases, the margin of error also increases. Firstly, what is the formula behind the standard error? Well, if we see here, standard error is equal to simple standard error. Okay, I mean, we are taking some sample from population and we calculate this standard error. Okay, divided by root of number of samples. I mean, each time we are taking samples from population and we try to calculate the standard error and see if we are taking, for example, 3 or 4 samples from this population, we can calculate in the standard error. So as we see here, as the standard error increases, that means we have this positive relationship. I mean, if standard error is increases, it's also the margin of error also it will be increases. If standard error is decreased, that means the margin of error also it will be decreased. I mean, we have strong relationship here. Okay, and this is the formula how we calculate the standard error here. I mean, here for standard error we take in, it means, or we take a samples from population, we calculate the standard deviation and we divide it by the number root of samples we have. It will be 4 or 5, that's depends. So question 3. So what is the proportion of confidence interval that will be containing the population parameters? Here we mean by that the alpha or the rate of risk. Okay. Here, so what is the proportion of confidence interval that will be contain the population parameters? I mean, if we have the parameters of population, I mean the mean of population and standard deviation, what is this proportion of confidence interval not be content these parameters of population. Alpha, that's parameter is called alpha. Alpha is the portion of confidence interval that not will be contain the population parameters. And to calculate or to found this value of alpha, alpha equal to 1 minus confidence interval. I mean, by default, we are taking, and most of the time, 95%. That means the rate is 5% because 1 minus 95% is equal to 5%. As I told you before, that's different of requirement of the test we have. If we have the area of telematics or drugs, or that's different. So it will be careful about this rate of risk. So this is formula how we use it or how we calculating the alpha one minus confidence under what we have. So most of the time it's 5%. Okay. Well, what is the difference between 95% confidence level and 99% confidence level? But what is the difference between that this rate and this rate? The confidence interval increase as move from 95% confidence level to 99 confidence interval. I mean, this relationship or the difference between 95% and 99% is increased. I mean, we we have this rate of 95% and we increase to 99%. Okay, that's depend of course the kind of test we have or test sorry we have. Okay, well, and 9% that mean we have just 1% of rate of risk. Okay, that mean the parameters of population we test is reviewed in this confidence interval. Okay. Question 5. What do you mean by degree of freedom? Okay. So degree of freedom is defined as number of options we have. Degree of freedom used in T distribution and not in C distribution. Well, we use in the T distribution if we don't have the parameters of population. So in most of time, of course, we don't have the mean of population. We can have just the standard deviation, something like that. At this time, we can use this T distribution. We have formula to calculating this T distribution. And Z distribution, of course, if we parameters of population is provided. So for a series, degree of freedom equal to n minus 1. I mean, we have n minus 1, where n is the number of observation in series. If we try to assist in something, okay, we are looking for this the number of observation we have. So if we are taking example of we have 50 observations at this time, the degree of freedom is 50 minus 1, that means is 49. If you have 13, 13 minus 1 is 20, 29. Okay, I mean degree of freedom is the number of the observation minus 1, and this degree of freedom we use it in T distribution. Okay, I mean the parameters population are provided. So question 6, what do you think if degree of freedom is more than 30? Okay, because in most of studies here, so we when we try to make or to when we try to lead or make some test, at least we the number of observation is will be more than 30. Okay, in most, so at least 13. Well, as degree of freedom increases, the T distribution research closer to the normal distribution. I mean, if we have this degree of freedom, it increases. That means the T distribution we have, the test of T distribution we calculated, it will be closer to the normal distribution. As we know, in most of time, we try to find this or make this transformation to the normal distribution. At low, uh, at low degree of freedom, we have fat gel. If the degree of freedom is more than 13, then the distribution is as good normal distribution. Is as good as normal distribution. Well, I mean, if the degree of freedom here is more than 13, at this time the distribution is will be good normal. So for this reason, in most of tests, So we need more than 30 elements or more than 20, yeah, more than 30 elements in samples. Well, if we see the question 7 here, when to use T distribution and when use to Z distribution. Well, the following conditions must be satisfied to use Z distribution. Well, what is the conditions we need to have if we try to using this Z distribution? So the first one, we know the population standard deviation. So to use Z distribution, the first thing we should have in our exercise or in our test is to have this standard deviation of population. Okay, this is the first step or the first conditions or the first criteria we should have. The second thing is the example size is more than 30. As I tell you before, we need more than 30. Okay, we have the first one, standard deviation of population. The second one, size of sample, it should be more than 30. And the third one here is the confidence interval is equal to x bar minus z times standard deviation divided by the root of n or number of samples we have. This is the confidence interval to calculate it because we have both left and right here. To calculate in the standard deviation, we need x bar minus z, how much the number or the value of z times standard deviation. Yeah, divided by the root of n 2. Okay, because this is interval will is starting from one place to another one. Here this is the left part. The second part here is x bar plus z times standard deviation divided by a root of n. N is the number of samples or element samples we have. Else we should use t distribution. Else that means we don't have these conditions. Okay, and most of times we use t distributions. Well, to calculating the confidence interval here is x bar, just we have the mean of these samples minus t. T is the value of t, how much after we look in the table of t and z table, okay, times s, the mean standard deviation of population, okay, divided by root of n, the number of samples we have, 2 x bar, okay, plus t times s standard deviation of samples divided by the root of n or a number of elements we have in our sample. Well, if we look in this next question here, 8th question, what is each 0 and each 1? What is each 0 and each 1? That is very important because uh, if we look in the inference, the her or the her, yeah, the her of inference statistics is this hypothesis. So what is each 1 and each 0? What is each 1 and each 1 for two tilde test? Well, each one is known as null hypothesis. So in inference statistics, when we try to lead some tests, this time we have two options or two tests. We have by default one, it's each one, it's called null hypothesis. It's normal case, okay? It's default case, normal case, it's each one. For one tail test, it's x is less or equal to mu. One tail test, I mean, we try to measure some means or something like that. Okay, and we have just one side. Okay, this value of x should be less or equal to mu. A is the average. For two tail test, both of the curve. Okay, well, because we have the curve, if we look in the curve, if we try just to find in one tail test, at this time we can look in for right or left, that's depend. But if we have two tail tests, at this time we have x equal to mu, that means we have left and side, left and right, okay? If we look in this curve like that, we can looking for right and side, and at this time we can calculate it and see what is the values of all these things. So that's for each one, I mean the default case, and for each one, sorry, for each 0. So for each one is alternate hypothesis. I mean, if we are calculating the for each one after we after the calculation we found it some values is not respect criteria at this time. We can reject this initial hypothesis and go to alternate hypothesis. Okay, so each one is alternate hypothesis is the other case. I mean, if that criteria is not respected at this time, we can go to alternate hypothesis. So as we look in here for one tail test, x is greater than mu. So is not. So if we look in this for each one, there is this logic behind this one test. We have x less or equal to mu, but here x is greater than mu. And for total test, I mean we have x different to mu, but here is equal to. Okay, here for by default case here is equal to, but here is different. This is the whole difference between the alternate and null hypothesis. Well, we have some types of hypotheses. Okay, well, so if we look on this type one here, we have sample hypothesis examples. A simple hypothesis predict the relationship between two variables. I mean, if we try to apply this kind of approaches, we need to consider some variables. At this time, we try to discover the type or the kind of relationship exists between two variables in this case. So the independent variable and dependent variable. I mean, we have two variables, one dependent and the other one is not dependent. So the relationship demonstrate through these examples. So if we look in these examples here, okay. So drinking sugary drinks daily leads to being overweight. Okay. So we look in the level of drinking sugary here in the okay. Well, drinking sugary drinks daily leads to being overfeed. So if you look in this, we try to extract here the hypothesis or default or the normal hypothesis. I mean, null hypothesis and the alternate. I mean, we try to see if I drinking sugary daily, thus it will be leads to being overfeed, yeah or not. And the other examples here, smoking cigarettes daily leads to lung cancer. If I smoking every day, what is the rate of to be lung or patients of lung cancer? Okay, and the third example here, getting at least 8 hours of sleep can make people more alert. Okay, what is the rate here of if I get at least 8 hours of sleep? Okay, eight hours of sleep. What make people more alert or not? Yeah or not? We need to calculating that to see if our hypothesis is accepted or rejected. So we have other types here is more complicated. Complex hypothesis examples. A complex hypothesis describe a relationship between variables. At this time, here is no one, maybe two or more. However, is the relationship between two or more independent variables and two or more dependent variables. I mean, we have more than two variables. It maybe can be dependent, maybe can be dependent. So we can follow this example to give a understanding of a complex hypothesis. So if we look in these examples we have here, adults who drink sugary beverage on daily basis, and okay, adult with drink sugary is the first variable, drink sugary beverage on daily basis, and have a family history of health issues are more likely to become overweight and develop diabetes or other health issues. So if you look in this sentence, it's content more than variable. Okay, first drinking sugary. Second one, maybe we have family history of health issues that are more likely to become overweight. The third one here is develop diabetes or other health issues. So we should consider all these things. And if we look in the second example we have here is in complex hypothesis example, individual that smoke cigarettes and live in large cities are more likely than others to have respiratory problems because of pollution. and increase the risk of cancer. Well, if you look in other sentences, it's content more than variable. Smoke cigarettes, life in a large cities is not a small one, so are more likely than others to have respiratory problems. So respiratory problems, it's coming because of pollution, because pollution in the in the large cities, okay, cause of pollution, okay, and increase the risk of cancer. Okay, how does two both of factors can contribute to increase the rate or the chance risk of cancer? Okay, well, if you look in the other one, null hypothesis examples, a null hypothesis denoted by each one propose that two factors or groups are in related and that there is no difference between content characteristics or population or process. You must test the likelihood of the null hypothesis. That means we just to consider this likelihood. So in tandem with an alternative hypothesis in order to dispose or discrete it. Some example of an hypothesis include, so if we look in this example of an hypothesis, so there is no significant change in the person's health during the times when they drink green tea only or both beer only. Well, here is example of an hypothesis. So how that change can have in a person when drink green tea or a root beer only. Second example here, there is no significant change in individual work habits where they get 8 hours or 9 hours of sleep. So we are kind of looking the change of behavior of person based on the hours or number of hours of sleep. So where they get 8 hours or 9 hours of sleep. So we try to measure that by this inner hypothesis. So if you look in the third example here, there is no significant change in the growth of a plant if one uses distilled water only or vitamin-rich water only to water it. Well, we need also to measure the growth of plants based of kind of water we have. Okay, where water rich with vitamin rich or just distilled water only. So it's kind of test hypothesis or null hypothesis we have. So for alternative hypothesis denoted by H1 or HA, it's a term that is contradictory to the null hypothesis. I mean, the alternate hypothesis is contradictory to H1 or H null hypothesis. So researchers will be pair the alternative hypothesis with the null hypothesis in order to prove that there is no relations. If the null hypothesis is disproven, then the alternative hypothesis will be accepted. If the null hypothesis is not rejected, then alternative hypothesis will not be accepted. That means we have a relation between null hypothesis and alternative hypothesis. If each one, we mean null hypothesis is accepted, at this time the alternate hypothesis each one, it will be rejected. If H0 null hypothesis is rejected at this time, each one, it will be accepted. Some examples of alternative hypotheses are a person's health improved during the times when they drink green tea only, as opposite to both beer only. Okay. Work habits improve during the time when they get 8 hours of sleep only, as opposite to 9 hours of sleep only. And third example, the growth of the plant improved during the time when it received vitamin-rich water only, as opposite to distilled water only. Here, in these examples we look in, we approach alternate hypotheses. So here, the green tea. So first one here is during the times when they drank the tea. Here we tracing 8 hours, and here we are tracing the vitamin-rich water because it's same last examples with H0 or null hypothesis. We just here tracing the second part. We mean the alternate hypothesis. Empirical hypothesis examples. Empirical hypothesis or working hypothesis come to life when a theory is being put the test using observation and experiment. I mean, here, if we are trying to derive some kind of test like that, this time it will be using observation, and this observation is able to experiment. So it's no longer just idea or notion rare. It's going through trial and error and perhaps changing around these independent variables. Reservoirs with liquid vitamin B grow faster than the rows were with liquid vitamin A. Sorry, here we try just making some testing. Two parts, okay, have that and that, and try to make measures and see what is right one. So woman taking vitamin A growth here faster than is taking vitamin K. So here, if you're looking, we have two parts. We have test. We need to drive test here. We have observation, and we try to prove this observation by experiment. And here it's last one, statistical hypothesis examples. A statistical hypothesis is an examination of a person or population or statistical model. I mean, statistical hypothesis, we apply this kind of test just in a person of population. I mean, we take in samples. Okay, we take in a sample. So in this type of analysis, you use statistical information from an area. For example, if you wanted to conduct a study on the life expectancy of people from savannah, so we take in this example of savannah here. We try to see the life expectancy of people from savannah. You would want to examine every single region of savannah. I mean, we are taking each single person in this population savannah. Is not will be practical, as I said before. There is no ability to work in the population. So for this time, this concept of sample it's coming. We take in samples each time and try to see the measure, standard deviation, mean, and all the measures and the parameters we want. So therefore, you will not conduct your research using a statistical hypothesis or a sample of savanna population. I mean, we take in just samples from savanna and try to draw some conclusions based on these samples we have. 50% of savanna populations live beyond the age of 70. Okay, here are some examples here. Just we draw these conclusions based on samples from population of savanna. We have 80% of US population get divorced because of being recountable or accountable. We have 45% of poor in the US are illiterate. Okay, 70% of the poor in the US are illiterate. So just we take in some examples and try to draw some conclusions. So we can take in any problem we want, and uh, so we have the ability to apply these concepts to draw some conclusions. So if we look on the process we have in Morocco, for example, maybe more than the 300,000. So it's a huge number compared to the population we have. Well, maybe it's 33% of rate will be divorced. Maybe of this information provided by the Department of HCP. Okay, so we can lead and draw a global conclusion just when using symbols. So this is the role of statistics. This is the power of statistics, and that is very important. And I can show you that how that is important when we try to work in real examples. Okay, just now I try to give you idea about this stuff and these materials, how does it work. After the session of practice, I will show you the okay using Python first, and that is very important. We should build in an idea about that. Okay, statistics is important concept in our life, really. That help us to make any decisions. That help us also to draw a big picture for any problem we want or any problem we have. Before trying to jump in deep of this data science or machine learning or IA in general. Okay, everything it's different. So it's like a chain. Well, happy learning for each one and see you again in next session. Thank you. Happy learning for anyone.